Welcome to another video for General Science. We're discussing gravitational force in this video. So Newton's fame isn't for his discovery of gravity per se, but for recognizing that gravity is universal. It works throughout the entire known universe, so every object in the universe attracts every other object, including you. You have a gravitational force, but it's so small that it's negligible. We don't really consider it in problems for the most part. So here I have the general equation for universal gravitation is the force of gravity is proportional to big G, our gravitational constant, which we'll talk about in a minute, the mass of the first object times the mass of the second divided by the distance between those two, the distance between the two center points, or the radii, squared. Okay? So let's take a look at this. So F represents the force between the two objects. Our G is a gravitational constant, which is 6.67 times 10 to the 11th power. Okay, I'll make a separate video as to how big G was discovered. Now remember, big G is different than lowercase g, which is gravity. This is gravitational constant. This is an incredibly small number. So this is a very small number of pool of objects, and this is constant throughout the universe for every object. So to find the gravitational force, we also look at the mass of the two objects, mass 1, sub 1, mass sub 2, and we divide it by the distance between the two centers squared. Okay? Alright, so here's our general equation again. I'm going to show you right now how we derive the unit for force, which is Newton. So if I look at G, so G times my other term, these are the units for G, our gravitational constant. It's Newton times meter squared divided by kilogram squared. So I know for, on my other term, mass 1 and mass 2, those are both in kilograms. And then my distance is measured in meters, so that's meters squared, right? Now, so as I multiply these out, I notice that I can cancel out a couple of my terms, like my meters squared, my kilogram squared, leaving me with just n by itself. And n happens to be the unit for force. And in this case, more specifically, our gravitational force. So that's how we derive these units. The math works. So what Isaac Newton was noticing and studying and calculating back in his day was very precise. Now, I should say that the gravitational constant wasn't discovered by Isaac Newton. It was discovered by someone else called Henry Cavendish. Like I said, I'll make a video of him separately and how he did that. But what's interesting is that what Newton found was very close to what Cavendish did. So without any advanced instruments, Newton came really close to what Cavendish found specifically. So think of the equation in terms of proportionality. Now we discussed this in a previous video as well. So assume now that the denominator remains constant. Assume that the distance between these two objects does not change. So if the numerator, if the mass, if the overall number increases, then that means the overall gravitational force increases. It actually makes sense if you think about it, because the more mass an object has, the more gravity it will exert on another object. And we've discussed that principle in a previous video as well. Now assume that the numerator remains constant. Assume that the masses remain the same. And now we're looking at distance. So just in mathematical terms, if the denominator increases, the overall fraction approaches 0. As an example, when I have 1 over 1, that's 1. 1 over 2 is half. 1 over 3 is 0.3 repeating, 0.25. And you notice that the number is getting smaller and smaller as my denominator gets larger. Okay, so I'm approaching 0 as my denominator increases, right? So that means the overall gravity decreases in terms of our physics problem here. So mathematically it makes sense. Philosophically it makes sense. It's pretty cool. Now here's the thing though, let's go back to this. You notice that my d is squared, my distance is squared. So in actuality, I don't have a nice consistent decrease in force as my objects get further away from each other. The amount of force that they exert on each other actually exponentially decreases as they get further and further away. As an example here, I have 1 over 2 squared, that's 0.25, as opposed to just 1 over 2, which is 0.5, and 1 over 3 squared, which is 1 over 9. So you'll notice that there's quite a bit of a drop-off, more than 50%. and then 1 over 16. So I'm approaching 0 exponentially, really fast. So the further objects get away from each other, the less and less attractive pull that they have. Now, do they still have an attractive pull? Yes, they do. It's just very minuscule. Okay, now 1 over the 49th. Okay, you'll notice that my number is really small. So here's an example of problem. Let's say Newton has a mass of 70 kilograms. He's on the surface of the Earth, which has a mass of 5.98 times 10 to the 24th kilograms. And the distance of the center of the Earth, remember, our d is measured from the center of our two objects, right? So we're measuring from the center of the Earth to the center of Newton himself. And that distance is 6.38 times 10 to the 6th meter. What is the gravitational force acting between the Earth and Newton? So Earth is pulling on Newton, he's pulling down the mass, and Newton is actually exerting a pull on the Earth as well, but it's of course much smaller than the Earth is on him. And then we have our distance. So here are our givens, here are our units. So when I look at my formula, I know that I have my two masses, my Earth and my person, and then I have my distance squared, and then my gravitational constant, that's always going to be the same, 6.673 to the negative 11th power. And all I got to do is do my arithmetic, and I find that the force that's being exerted is 686 newtons. Okay. Now, if you go back to our previous video where we talk about weight, if you do the mass of Newton times the acceleration of gravity as well, you'll notice that you'll get the same. So this physics problem actually works across the board. There's no inconsistencies in the math. Now, what would happen if Isaac Newton were on a plane 40,000 feet up? Well, first of all, I'd have to convert feet into meters, right? So if you take a look at the denominator position for my problem, you'll notice that it's going to increase. It's going to increase because the height has increased. He's now further away from the center of the Earth. Okay, so I went from 6.38 to 6.39. So he's just a little bit further. Now, as you noticed, that was a very small number change. 40,000 feet away from the surface of the Earth is a really minuscule distance compared to the radius of Earth itself. Nonetheless, I'm still going to do my arithmetic, and I find that the force compared to Isaac Newton on Earth, on the surface, which is 686, to him being on an airplane is 684, it's a difference of 2 newtons. So it's a very minuscule difference. Okay, you can be in Mount Everest and gravity will have less of an effect on you, but it still has an effect. You're not flying off into space. It's a negligible difference, but a difference nonetheless. So you can actually use this formula to find the gravitational pull for planets like Earth and the stars with the moon and orbiting bodies like the moon and stars like the sun. Now, this is not the scale. If this was the scale, it would look more like this. But nonetheless, there's a gravitational effect that each of these orbiting bodies have on each other, and you can use this formula to find that. So to find the force of gravity and that the sun is to the Earth and vice versa, it's the same as to find the gravitational pull of Earth to moon. In fact, the moon and the sun have gravitational pulls on each other, and you can use this formula for that same purpose as well. Just have to find the mass of the moon and the sun divided by the distance squared times gravitational constant. So remember, this is, after all, called the universal gravitational force, meaning that this is a force that's ubiquitous. It's universal. It's consistent with everything we know of the known universe, and thought to be one of the causes of the fact that everything is kind of staying. All the known universe is maintaining its stable position for the most part. Now it is expanding gradually, but for the most part the universe is pretty stable because everything is exerting a force on each other, and it's just kind of keeping everything in place. Well, that's a very simplistic view of what's actually happening, but nonetheless it still applies. And thanks for listening, and good luck with your studying.